Hello guys. So, today to start our discussion to continue our discussion on analysis of variance, we have almost covered the required concepts of Anova. Required concept of Anova, by that I mean only one way Anova, because we have just discussed one way Anova. The two way Anova, three way Anova, multi way Anova, and all this I have not discussed. As I told, once you know the one way Anova, you will be able to learn it by yourself only, and moreover it is really difficult to teach all those in a classroom, and because intense computation is required for that. However, the concepts are the same. With the same concept, we will be able to do the rest. So, now in today's class, what we will be doing is that we will be seeing some examples. Okay, we have learned the applications, we have learned the concepts. Now, we will see how we will use those to solve the problem. The first problem that I have the first example that I have taken is, it is not an that contrived data, that data which we have just created. It is not any not an example as such. We have remembered this data we have used to come to the conclusion that why when we want to compare means of different population, why do we need Anova. We have used this example for that purpose, and now first example we will try this only. With this example, we will see what Anova gives, what result does Anova gives in this contrived set of data. So, if you can remember properly, there in that last class, I think in the first class on Anova, what we have discussed is that there are two sets of data, that is set 1 and set 2. And we see there are three different, we have taken 3 samples from 3 different population. Maybe we have taken from 3 different population, or maybe not, we do not know. Like we have to prove that whether all the populations are really different. That is, whether the means of the populations are really different. That is what we wanted to prove. That was our objective. So, since we see here in the set 1, sample 1, we got the mean of 6. Okay, first let us see that what we got in sample 1, we got mean 6, sample 2 we got mean 10, sample 3 we got mean 15. Okay, this is quite a difference, quite a significant difference in the all the 3 samples. Now, if we just tell from the mean, yeah, we can see that, we can tell that, yeah, the means are really different. That means these 3 samples are taken from 3 different populations having 3 different means. If we just see the means, from the means we can say that. Similarly, in the set 2 also, set 2 we see the set 2 the mean of sample 1 is same as the set 1 mean of sample 1. Then mean of sample 2 of set 2 is same as mean of sample 2 of set 1. Similarly, for set 3 also. So, that is why we could also tell, okay, fine, for even for set 2 also, all the 3 samples are from 3 different populations whose means are different. In fact, if we can just from the means, we can say maybe that for both set 1 and set 2, sample 1 of set 1 and sample 2, maybe it is from the same population. Again, sample 2 of both set 1 and set 2 may be from the same population. Similarly, for sample 3 for both set 1 and set 2 may be from the same populations. Means 3 different populations. From one population we have taken sample 1 for both set 1 and set 2. For another population we have taken sample 2 for set 1 and set 2, likewise. So, if we from just looking at the means, we could come to that conclusion. So, now remember, we were not very much convinced with that, because this difference in means may be attributed to many other factors. That is what we have discussed earlier. So, what we have tried to do, remember, we have plotted a box plot for this. So, when we have plotted the box plot for this set of data, what we saw is that for this sample 1, I do not have the figure right now with me, it is in the first slide of the Anova's lecture, first lecture actually basically. So, what does the box plot indicate? Box plot indicate the 3 samples of set 1, there we could see they are very closely punched together, and that means the variance among themselves within variance within the sample was very less, and from the box plot we could very easily say, yeah, this 3 sample 1, sample 2, sample 3, these 3 may have come from different populations. But same we could not say for set 2, because it has a very huge variance. It was as if from the figure, as if we can say that as if it has come from a single population, 3 different samples, but it has come from a single population. It was its variance is so high for all the sample 1, sample 2, sample 3. That means we could tell that okay, for set 1 the 3 means are different, but for set 2 we could not say that the 3 means are different. Why? Because we know from sampling distribution of mean, we know that if the variance is high, if we have a high variance, that the mean of the sampling distribution is equals to the population mean, that statement is not a very precise statement. Reliability of that statement is not high. We cannot say with accurate precision that the sample mean is equals to the population mean when the variability is quite high. Variability indicates the standard error among different means, right. Sampling distribution of mean means what? Sampling distribution of means the different means of different samples, isn't it? So, now the same example now we will use to do this. We will be using the same application to find out using Anova whether what we got from the box plot is that the same result we get it or not. Let us see that. So, first thing is that if we try doing the Anova, first what we need to find out for that, you remember Anova thing. So, if you can remember what was our f, value of f, we need to find out the value of f, right. So, what was f? If you remember correctly, f is MS treatment by MS error. This MS treatment was the difference of treatment mean from the grand mean, and MS error is the for all the samples. Basically, we try to find out the variance within the sample. So, if you just a quick recap. So, what was the formula for MS error? We call it MSE basically. So, what was MSE? MSE is equals to summation of I is equals to 1 to A, indicating that there are total A levels, then summation of in each level how many data, j is equals to 1 to n. So, y I j minus y I dot bar whole square, okay, and divided by the I is equals to 1 to a n minus 1. Remember, this was the formula for MSE. Basically, if you can this also you can write it. It was nothing but a pool variance estimate also. This thing we can also write it in this way: n minus 1 s square plus n minus 1 s 1 square, basically s 2 square plus n minus 1 s I square, then n plus 1 plus n plus 1 plus n plus 1. This is equals to this, we have seen it, isn't it? What is this n plus 1 up to total how many levels? For till A levels, and this s 1 square is the variance of the individual level. So, n is the number of data in each sample. Here the samples, all the samples are of same size, that is n. So, this is thing we have already seen it. So, this is how we can calculate MSE. We can either calculate MSE by this formula, or we can calculate MSE by this formula, whatever is. This is the same thing, from this we got this. And similarly, what was MST? MS treatment, that is MS treatment is equals to SS treatment divided by A minus 1, that is the level minus 1, and this is what was that, n at summation of I is equals to 1 to A. It is the sum of squares of this treatment means from the grand mean. So, it is y I dot minus y dot dot, this is the grand mean y dot dot whole square divided by A minus 1. So, this was our formula, remember. So, now, for this sample set, if we first thing is that we will calculate what is that MS treatment or MS treatment as well as MS error. So, if you want to calculate MS treatment, what you need to do, I will just find out the variance from this. From each sample I will find the variance. So, n minus 1 this is, suppose this variance is s, okay. Suppose this variance is s 1 square, this variance of this is s 2 square, variance of this is s 3 square. Okay. So, what is how many 1 2 3 4 5, 5 is n is 5. So, n minus 1. So, n minus 1 s 1 square, n minus 2 s 2 square plus n minus 1 s 3 square divided by how much, n minus a. n minus 1 plus n minus 1 plus n minus 1, that is n minus a n minus 3. So, that way we will get MS error. Similarly, we can find out the MS treatment. MS treatment formula is this: the treatment we will find out the treatment mean, this is the treatment mean, find out what is the grand mean of that. Grand mean is 6 plus 10 plus 15 divided by 3, that will be the grand mean, is not it. So, from the each mean each treatment mean will subtract the grand mean for all the levels, then divided by the degrees of freedom. So, that way we will get the values. Of course, the first thing is that we need to know what is the hypothesis. We will be able to solve it using the hypothesis testing only, is not it. The first thing is what is the hypothesis. So, for us the hypothesis is mu 1 is equals to mu 2 is equals to mu 3, that means all the populations comes from the all the means of all the 3 populations are same, that is the null hypothesis. Alternate hypothesis is at least 2 of the means are not equal. Okay. So, for that we will have to find out the F ratio. So, if value of F falls in the critical region, then we reject the null hypothesis. If the value of F does not fall in the critical regions, then we cannot reject the null hypothesis. So, by doing this calculations, we got MST is equals to this, MSC is equals to this, and we got the value of F is this. For this is for the set 1. Set 1 we got this value. Similarly, we will do for set 2 also. Set 2 we got this value. F value, you see F is equals to 9.53. Now, directly from seeing the F value only, you can make it out the difference. See F, remember F distribution is something of this sort, and mode value of F means it is going this way. Mode value of F means F will be this way, and F is 9.53 means F is very much in this range, is not it. And as I told you, for Anova, remember it is always a one tail distribution. We are only interested in finding out if it is greater than, we are not interested in finding out less than. So, because if the means are all the means are not same, that means our MST value will be quite big compared to the MSE value. So, if MST value will be big, that means for more MST value is more the bigger, more the value of F. So, we are not interested in finding out the lower tail, isn't it. So, lower tail when we will get, when the MST value is less, then only we will get the lower tail, and MST value will be lesser than the MSC value, that is very unlikely. We are not interested in finding that. MST value will be bigger when the treatment means are different, isn't it. So, we are only interested in the upper tail. So, here what is the rejection region if we consider at 5% significance level. So, at 5% significance level, what is the degrees of freedom here? Degrees of freedom is for MST, what is the degrees of freedom? MST degrees of freedom is A minus 1, that is total level is 3. So, degrees of freedom is 2, and for MSC degrees of freedom is n minus a, n is 15, total that is 15, 15 minus 3 is 12. So, our degrees of freedom is 2 minus 12. So, if you see the F table for 5% significance level, see here we will consider alpha is equals to 0.05 only, we will not take alpha is equals to alpha by 2, we will not do alpha by 2, because it is single tail, it is not two tail. So, if we see the table for that, we will get the this is the value. It is 19.41. 19.41 is the means if it is greater than 19.41, then it falls in the critical region. And see what is our value of F for the first set, F is 406.67. It is much greater than 19.41. It is very much in the critical region. Even our box plot also saw it. From our box plot also we could see that, right. And for the set 2 we got in the acceptance regions 9.53. So, though the means of both the sets are same, but still for set 1 we could very conveniently say that all the means are different for the 3 different population, null hypothesis is rejected, and for set 2 null hypothesis we could not reject the null hypothesis, we do not have enough evidence to reject the null hypothesis. Okay. Clear, that is how we do the Anova testing. So, it appears that there is a stronger evidence of difference among means in set 1 than among means in set 2. Stronger evidence, it is very much in the critical region. This confirms the relative magnitude of the two variants is the important factor for detecting differences among means. We have already seen that, isn't it? That's why only we have learned ANOVA. This was the why we need to do ANOVA just for our justification. We have seen this example. Now, so let us take another example. Here, the table below, it shows the lifetime under control condition in hours in excess of 1000 hours of a sample of 60 watt electric light bulbs of 3 different brands. 3 different brands of lights are there. It is so it gives us the life hours, life of the bulb in excess of 1000 hours. So, we need to find out whether the 3 brands are same or not. The means of 3 brands, the lifetime of all the 3 brands are same or not. So, our null hypothesis is mu 1 is also mu 2 is equal to mu 3. Alternate hypothesis is at least one of mu 1, mu 2, mu 3, at least 2 are not same. So, that is the alternate hypothesis. So, we have to test at 1% significance level, that means 0.01. So, what are the hypotheses here? Hypothesis is mu I is equal to mu I for all I is equals to 1 to a. How many a here? A is equals to just 3. Okay. So, then alternate hypothesis is at least one equality is not satisfied. So, we have to reject A 0 if the calculated value of f exceeds alpha confidence level of the f distribution with a minus 1 and n minus a degrees of freedom, isn't it? MS treatment degree of freedom is a minus 1, MSE degree of freedom is n minus a. Remember when we have learned f distribution, that time it is a general convention. In the table it is given that the table follows all the standard textbooks. In the table it follows that for the greater the numerator which is bigger, we keep it in the value of the variance which is bigger, we keep it in the numerator. That was while trying to compare populations variance of 2 different populations, but for when we use f distribution for ANOVA, then we do not have to find out which one is bigger and which one will keep in numerator. Always the numerator will be MS treatment, because if there is any difference in the means, definitely MS treatment will be more. If there is no difference in the mean, MS treatment will be almost similar to MSE. With of course, there will be a slight difference, but it will be almost similar to MSE. So, we do not have to bother whether we will have to put the bigger one or smaller one. Always MS treatment will be MS treatment will always be bigger or maybe similar to MSE. So, an MS treatment is always put in the numerator. So, now there is only one factor. What is the factor? The different brands, and the 3 levels 1 to 3, and the sample size is equals to 5. First we will find out the sample. This is a good way. This actually this why I have solved it this way. Any given problem on ANOVA, you try to solve it this way. Just make a table, because then it becomes very easier to calculate. Make a table first, and then different levels, put the different levels, then sample size for each. Of course, now we are discussing the sample size is same for all the samples of all different populations. Then find the sum of all the samples values. Sum of all the sample values means this value, sum of all these values, sum of all these values, sum of all these values. Okay. Okay. So, this is the sum. Then sum of squares. Sum of squares means what is the sum of squares? Actually here I did not mention it very properly. Sum of squares, there are sum of squares of different types. One is the when we are trying to find out the sum of squares within the variance, isn't it? I mean within one sample. That how do we find out the sum of squares of that? That is we take each data of a sample, subtract it from the mean of the treatment, isn't it? Each data of the treatment, subtract it from the mean of the treatment and square. That is the sum of squares for each treatment, and that is within group sum of squares basically, and one is between group sum of squares. How do you find the between group sum of squares? So, basically it is better if you have 2 column here. One is within group sum of squares, and next is between group sum of squares. And between group sum of squares, how do we find out? That is, we will subtract treatment mean from the grand mean and add up all those. Will suppose we have 3 treatments, then treatment mean of the sample 1 minus grand mean plus treatment mean of the sample 2 minus grand mean plus treatment mean of the sample 3 minus grand mean. of course square. So, that is sum of squares between treatment. So, instead of one column here which I have shown as one column, and so it is always better if you do have it two columns, sum of squares between groups and sum of squares between group. Then is the mean, then you find a variance. Now, since once we found a variance, finding out the MSE will be very easy for us, is not it? What is MSE? MSE is n minus 1 S1 square plus n minus 1 S2 square n minus 1 S3 square, how many, and divided by n minus a. So, it will be very easy for us to calculate MSE. So, that is also called pool variance estimate, if you remember. So, that is how. So, it was so easy once you calculate the first, you calculate the variance, else if you try to do that first, it at the first glance it may seem it is very complicated, but it is no, just find the variance of each sample. Once you find the variance of, first find the mean of each sample, variance of each sample, and then once you have the mean of each sample, then you find a grand mean. Grand mean is nothing but the mean of all divided by the total number of means. Then finding out the sum of squares also becomes very easy. Sum of squares within the within sample, when you are calculating variance, you already calculate that, isn't it? What is variance? Variance is equals to sample variance S square is equals to xi minus xi bar, x bar basically whole square divided by n minus 1. So, this is variance. So, when you calculate variance, already you calculate this sum of squares. So, this is MSE. So, what is MSE? MSE is the variance within samples, right. Then as we have already discussed, this is an estimate of, this is basically the pool variance estimate, isn't it? Pool variance estimate, and what is the degrees of freedom of that? Degrees of freedom is n minus a, small n minus number of levels. Small n is the sorry, not small n is the sample size. Capital N means sum of all the sample size, sample sizes. So, V is degrees of freedom is here, total number of item is 15 minus 3 is 12. So, now similarly you find MS treatment also. MS treatment, what will be the degrees of freedom for MS treatment? The degrees of freedom for MS treatment will be just the level minus 1, number of level minus 1, A minus 1. So, find out the value of MS treatment. So, here, so MS treatment I did not calculate it, and so you can do it very easily. So, it is 155. So, what the F statistics value we got 15.5, okay. And what was the significance level is 1% significance level. So, at the 1% significance level, from the table we using the degrees of freedom 2 and 12. What is 2 is the degrees of freedom of MS treatment, and 12 is the degrees of freedom of MSE. Using this degrees of freedom, if you see the F table, you will see that this value corresponding to this is 6.927. So, any value which is greater than 6.927, it falls in the rejection region or the critical region. Lesser than 6.927 means it is the acceptance region. So, what we got? We got our F statistics value is 15.5. So, it is 15.5 means it falls in the rejection region, right. So, that means it falls in the rejection region, means that means we have reject the null hypothesis. That means all the 3 brands are, once we reject the null hypothesis, definitely we accept the alternate hypothesis. So, that means the 3 brands are, population means of the 3 brands are different. There is evidence at 1% significance level that the true mean lifetimes of the 3 brands of bulb do differ. Fine. So, this is Anova. Anova, see, just understanding the Anova a bit difficult. Actually, it is not difficult if you try to understand it properly. If you please go once, if you cannot understand it once, please go through the slides 2-3 times. From slide number 1, Anova, I think I have covered until total 5 lectures, and today is the 6th lecture on Anova. Here we are doing problems. This 5 lecture, go through it again and again, and it will be very easy for you to calculate it. It is nothing. First, you should understand what does actually Anova does. First, you need to understand that. Basically, Anova gives us the Anova entity. The Anova entity gives us the 2 estimate of the variance. So, one estimate of the variance we get it from the difference of treatment means. Okay. Another estimate of the variance we get it from within a sample. What is the variance? These 2 variance, these are the 2 variance estimate. So, if the population means are equal, then what happens? Both the variance estimates are same, and if the population it may not be exactly same, it is similar value, and if the population variance if the population means are not same, then we will get a value which gives then MS treatment basically. That means the variance within the treatment, that is quite a big value, and which lead us to a F value which falls in the critical region. Okay? And if it falls in a critical region, that means we reject the null hypothesis. That is, null hypothesis means that all the population means are not same. So, we have enough evidence to say that all the population means are not same. So, now just to conclude this, in essence, given a population and a single factor of A levels, we have to calculate two estimates of sigma square. Sampling variance between treatment with A minus 1 degrees of freedom is MS treatment. Fine. Sampling variance within treatment with n minus a degrees of freedom is this. Fine. Then use F distribution to find the statistical significance of both the variance. Statistical difference of both the variance basically. So, in fact, this should be difference of both the variances. Okay. So, these are the references, mainly I am covering from design and analysis of experiment. Other books also, you can also refer to other books, and thank you guys, thank you.